This conference will now be recorded.
Hello students, we have been discussing wave optics. We had already discussed some part of it. We had covered up to interference of light, and there we had discussed Young's double slit experiment, YDSC, and then we had completed various types of numerical problems from previous year's JEE and NEET papers. Now today we are going to discuss about diffraction of light. So see, what is diffraction? In the very first class of this wave optics, we had discussed that wave theory was needed. Theory was inevitable, required, or inevitable to explain different phenomena of light like interference, diffraction, and polarization. So today we are discussing diffraction of light. So in the interference we have seen that if two light waves interfere, some places you will get bright fringe and some places you will get dark. Again you get bright, then dark, alternate bright, dark, bright, dark, etc. you get. But what happens here? So here, we had learned from the corpuscular theory. What corpuscular theory said? Corpuscular model of light. It says that light propagates in a straight line, or rectilinear propagation of light is possible. Okay, so this is actually the concept of ray or corpuscular model, that light will travel in a straight line. But you know what happens when light passes through a very narrow hole or slits or pinhole, or when it passes by a sharp edge of an obstacle, okay, then it is seen that light actually gets bent. Okay, light gets bent. Okay, instead of traveling in straight line, light gets bent, and eventually light enters into the geometrical shadow region. Okay, geometrically shadow regions. See, for this case, if I have this slit, so this is actually the opaque region. Like these sides are opaque, or this side actually I should not get any light, isn't it? But we get this. Not only that, so this is actually, see, this bending of light, the phenomenon of bending of light is actually called diffraction. This is actually an wave phenomena. Okay, this is an wave, like this is a wave phenomena. So diffraction of sound waves and other waves also possible. Okay, diffraction in case of sound wave and other waves also can be possible, and this light is electromagnetic waves. Okay, so both mechanical, electromagnetic, and maybe some other waves also can exhibit this diffraction phenomena. So let me tell you once again what happens when See, this is a slit. Okay, slit means you have some screen and just make a hole, narrow hole. This is not very narrow, this is wide little bit, but anyway, if you make a hole, you look, the light is actually getting bent, or see, light is getting spreaded. Okay, better you see here at this position. See, so this here, see, in general light should not be there, so this is shadow region. Okay, geometrically this region is shadow, but you know what we see? We see light in this shadow region also. So this spreading of light or bending of light while passing through very tiny hole or pinholes, passing through pinholes, or while passing by sharp edges of obstacles, then light gets bent. This phenomenon is called diffraction of light. So as you see here, the plane wavefronts here, and you know, after passing through this narrow hole, you see the diffraction or the bending of light, you can see. Okay, this is actually getting spreaded. See, like this it is going, isn't it? It is diverging, kind of diverging. Here also you look, the light wave is kind of diverging or spreading away. Here you can see this very well. Okay, light is spreading away, and wherever light should not go, according to corpuscular model, that is in the shadow region, the light actually is there in the shadow region also. But geometrical shadow region, what we will see? We will see alternate bright and dark fringes over there also. We'll see in case also, in this diffraction also, we'll see a wide or broad bright spot like this, and then alternately we will see maxima, minima. Okay, alternately we will see maxima and minima. Okay, or bright and dark regions we'll see. We'll see a wide bright regions, and on either side of this bright region, alternately we'll see bright and dark regions of decreasing intensity. So formally, if we want to define what is diffraction, so diffraction of light is a natural phenomenon where light bends around a sharp obstacle or an aperture, and as a result light spreads into the geometrical shadow regions and alternate dark and bright regions, just like interference are observed. So in case of this also we see alternate dark and bright regions, but in this case, you know, we'll see with decreasing intensity away from the central bright regions. Okay, we'll see a central bright region, and on either side we'll see the alternate dark and bright regions. Actually, if you see intensity distribution, we'll discuss sometime later. So we'll see that this will be wide bright region, and then alternately like this you'll see. Okay, so I think we'll see better figure later, but now let me explain once again what is happening here. Suppose this is a slit. Okay, see, the geometrical shadow regions are this. Okay, these are geometrical shadow regions. Okay, when the light wave is actually passing through this narrow slits, then you look, the light is actually getting bent at this sharp edge, at this edge. Okay, or the light is getting spreaded. Okay, spreaded we can say, and in this case also we can see at the sharp edge how light is getting bent. Okay, so this bending phenomena, bending is actually called diffraction of light, and at this regions of this, okay, this geometrical shadow regions, what we see? We'll see alternate bright and dark regions. Okay, all right. So what is the condition for diffraction effect, okay, to occur? See, the first and foremost criteria is that, so this also, so but actually what is the interference, like what is diffraction? just for now, I'll just tell you in a single sentence that this is also one kind of interference only. This is also kind of interference, but in this case, see, in Young's double slit we had Young's double slit we had two sources, right? S1 and S2. Okay. Now we'll see in single slit diffraction experiment we will have only a single slit. There we can see the diffraction. So in interference, actually the wave fronts. See here we will bring the concept of Huygens principle, concept of wave theory, and according to wave theory, each point on the wave front will act as secondary sources of light. So in case of diffraction, there will be many secondary sources which will actually produce secondary wavelets, and those wavelets interfere. In case of interference, wavelets from different sources, see, wavelets from different sources are interfering. Like from S1 is actually acting as a different source, S2 is acting as some other source. Like these two are actually different sources. Now wavefront from this and wavefront from this, they actually interfere. But in case of diffraction, see, this is the wavefront, and waves are coming from, suppose, this point and this point. So these wavefronts coming from the same wavefront, okay, the secondary wavelets coming from the same wavefront will interfere to give rise to interference phenomena. Okay, so here the first criteria should be monochromatic. Obviously the light must be monochromatic. Okay, light must be monochromatic, and second thing, the slit you use has suppose dimension A. This has to be less or equal to lambda. Okay, or in other words, very like crude way to say that this has to be comparable to lambda at least. So slit width has to be, or the obstacle aperture has to be of the dimension of the light used. Okay, the size of aperture or obstacle has to be comparable with the wavelength. Okay, wavelength of the constant wave. So this may be, so the two conditions are there for getting diffraction pattern. One is monochromatic light has to be used, and the slit width or obstacle size has to be nearly equal to wavelength of the light used here. Okay, so this has to be nearly equal. So this is the only phenomena. See whatever, see, visible light has 400 to 700. You can take 400 to 700 nanometer. Okay, 700 nanometer. That means how much? Of the order of 10 to the power minus 10 to the power minus 9 and 2. So this will be of the order of 10 to the power 7 to 10 to the power 6 meter. This is the wavelength of visible light. Okay, wavelength of visible light. So but in our like in the places around us, the objects are very large in size compared to this dimension, right? 10 to the power minus 7 to 10 to the power 6. This is the range of visible wavelength. Okay, visible, like wavelength of the visible light. So that's why we cannot see diffraction phenomena. Okay, diffraction phenomena to occur, so the aperture or the sharp edge has to have a dimension of comparable, like a dimension comparable to the wavelength of the light used. So that is why you have your window, and you have, see, the window has window has this rod, parallel rods, so sunlight comes through this, right? But diffraction phenomena is not observed, isn't it? Diffraction phenomena is not observed in this, like when the sunrise passes through the parallel rods, because the dimension of this gap is not comparable to the wavelength of the visible light, isn't it? So that is the reason why we see diffraction pattern. Why don't we see a diffraction pattern around us? Okay, so that is the reason. Okay, so I think I can refer to the first figure again. You look here, the diffraction. See, when the aperture is 6 times of lambda, then see diffraction phenomena or spreading of light is little less. When it is becoming half of that, that means 3 times of lambda, see, then we can see better bending, or we can see better spreading, or we can say we see better diffraction. Now when this aperture size is reduced to 1.5 lambda, see how great this spreading is, or how great this bending is. So diffraction phenomena will be prominent when the dimension of the aperture is nearly equal to the wavelength or comparable to the wavelength of light used. Okay, so now we'll see there are mainly two different types of diffraction, like according to like diffraction maybe. Okay, so the study of diffraction, I can say the study of diffraction we do in two ways or two methods. One is Fraunhofer diffraction and another one is Fresnel's diffraction. So this is related to experimental setups and all, and the apparatus we use. Okay, so Fraunhofer diffraction, in Fraunhofer diffraction what we do, actually we keep the source and the screen at infinite distance, ideally at infinite distance or at very large distance from the aperture. Okay, so source and screen, see this is the aperture. If I see this is the aperture, and see source will be here somewhere. Okay, source. So this source has to be kept at a very large distance, nearly equal to infinity. Okay, ideally it is infinity. So this is infinity, source to slit distance or close to aperture, and aperture to screen distance also ideally should be infinite. Okay, so at this case, you know, the wave fronts will be how the wave front will be. See, any shape you take initially for the wave front, but when they travel to infinite distance, then they will be eventually parallel wave fronts. Okay, so in case of Fraunhofer diffraction, the wave front, concerned wave front or associated wave front of the lights are plane wave fronts actually. Okay, and see the source and the screen are placed at infinity from the aperture or at very large distance from the aperture. And see, in this case, since the light is actually going to infinity, so to make them converge, okay, to make them converge at a least distance or like our comfortable distance, okay, actually length has to be used, because light will be going to infinite, right? Infinite otherwise, that means it will actually, it may not converge on the screen. That's why the in the experimental setup we use converging lens to converge them. See, actually then how will be the setup of the experiment here? See, there will be source here, then slit here. Okay, source slit. Okay, here also we can actually can use a converging lens just to make the light fall here. Okay, pinpointedly or something like that. Okay, now from here when the light rays are coming out, since this screen is at infinity, so they have to converge on the screen. So you should actually use, okay, you should use a converging lens again. Okay, so this is actually sorry, Fraunhofer diffraction. Now another type of diffraction study is the Fresnel's diffraction. So in case of Fresnel's diffraction, then the source and the screen are placed at the close to the aperture. Okay, source, that means the aperture, see, this is source, this is the aperture, and this is screen. So they will be kept close to each other. Okay, close to, that means source is close to the aperture as well as screen is close to the aperture. Now wavefront, in this case, since the source is very nearby, so you see the spherical wavefronts illuminating this slit. Okay, and the emergent ones also will be spherical wavefronts. Okay, all right. And one more thing is that, see, since the in case of Fresnel's experiment, Fresnel's diffraction study, the source and the screen is kept near to the aperture, we do not require any convergent lens over here. Now see, we'll see single slit diffraction. See, when a double slit, Young's double slit experiment, what we see in Young's double slit experiment, we had seen two slits, right? If we replace the whole setup with a single slit, then it is called actually single slit experiment. And here diffraction phenomena will be studied in the single slit arrangement. So when the double slit in Young's experiment is replaced by a single narrow slit and illuminated by monochromatic source of light, then a broad pattern at the center of the screen, we say, or we see a broad pattern with a central bright region is observed, and on either side of this central bright region, alternately bright and dark regions with decreasing intensity will be observed. The central bright region is called the central maxima, and the respective, okay, central maxima, and the dark and bright regions on either side of the central maxima are respectively called secondary maxima and secondary minima and secondary maxima. Okay, bright regions are called secondary maxima and dark regions are called secondary minima. Okay, so to understand the diffraction pattern, okay, first of all, see, understanding the conditions for getting different positions. See, as I said, we'll have, see, central bright fringe here like this, and then alternately we'll have like this. Okay, and here also this side you will see decreasing intensities. Okay, so these are secondary maxima. This is secondary maxima, this is secondary minima. I'll tell you why these are called secondary minima or maxima, and what physics is behind this. Okay, so first of all, see, we had this knowledge that in case of interference, constructive interference will be occurring when the path difference delta is even lambda. Okay, path difference is multiple of even lambda. Okay, multiple of even lambda. All right, that was actually for condition for bright fringes to occur. Okay, and for dark fringes to occur, see, path difference has to be multiple of, see, odd multiple of lambda by 2, odd multiple of lambda by 2. So if some cases, you know, the okay, so with this idea, let us try to find out this. See, from this experiment, so this is actually this experimental setup. You can see this is screen, this is actually aperture, and these are incident of waves. We are actually seeing here Fraunhofer diffraction. Okay, Fraunhofer diffraction means source is at infinite distance and screen is at infinite distance from the aperture. Okay, so with this assumption, we just see this experimental setup is actually for single slit. I'm sorry, I think I have missed one point here. Okay, so no worries, we'll just do here. Let me then draw the single slit experiment here. Experimental setup. This is single slit. I just make it little wider, even though this slit would has to be narrow. Okay, sorry. Okay, so you know here what is done. So source is here somewhere. Okay, then you know you will be using a lens over here. Okay, so that you get parallel rays, you keep this source at the focus, so you get parallel rays here. Okay, and those parallel rays illuminate, you know, to illuminate this, so this will come and meet here, right? So these are kind of parallel wave fronts. Okay, kind of not kind of, these are parallel wave fronts, and these are ray. I'm just showing you in terms of ray like this. Okay, now see, they will diffract means what? They will actually see, instead of going in straight line like this up to screen, okay, instead of going like this, they will be actually bent by some angle, say, sorry, they get bent by some angle theta, say, and see these rays are, this ray also will get bent by same angle, and they will meet somewhere at the same position, say. Since this screen is at very large distance, these rays will be actually parallel to each other, and you know, to make them fall, I'm sorry, actually there should be a converging lens over here, so that they will be converged on the screen. Okay, let me, I think this is too large too, sorry. The next class I'll show you the proper figure again. So here, okay, so maybe I'll just draw once again. Okay, great. Okay, So we can take any other waves from here also, that also will get bent like this and meet here. Okay, compared to this angle is theta, this angle is also theta. So those are actually parallel to all like each other. Okay, after diffraction, and that's why we need to use this length. Okay, this is L2, say this is L1, this is L1, to get the parallel beam to illuminate this slit. Okay, and this is screen. And see the rays which are coming to the central point of the screen. So this is central point C. So all the rays which are coming and meeting at this central position, they actually travel the same path. That means they have zero path difference. So if there is zero path difference, then what will happen? All of them will actually interfere constructively. So there will be a bright region over here. Okay, bright. There will be a large intensity. Okay, bright region, because all the rays coming from the slits or different parts of, see here also there will be a wavefront like this. Okay, wavefront. Okay, so from each point of this wavefront there will be secondary wavelets produced. As you know from Huygens principle, each point on the wavefront will act as a source of secondary waves. Okay, they will produce wavelets, and those wavelets are actually interfering. Okay, see actually in this case also interference is happening. Let us say this, the rays are meeting or interfering at the point P after diffraction. In the sense, okay, so these rays are actually interfering at the point P. As they are interfering, say this angle is theta. Okay, so whether, see as I said, the rays which are meeting at the central point of the screen, they don't have any path difference, so they will produce a central bright region, wide region, wide bright region. Okay, say this bright region, if this is the first one, say first minimum. Okay, let me draw it here itself. So it will have a wide region like this. Okay, wide region. All right, so wide bright region will be there, that is called central maxima. Central maxima. Maxima. Central maxima. And see, the on either side we said, on either side there will be alternate dark and bright. So you will see like this. Okay, alternate dark and bright regions will be produced. But now we are going to find out the condition for minima and maxima. Okay, condition for secondary minima. See, we have got central maxima. Now we have to find out condition for condition, or we have to find out positions. Okay, if I say this is, if I take the reference, then this position may be called as x. Okay, x or y, whatever you can say. So these positions, what is the separation between these two? What is the separation between this central maxima and first minima, secondary minima, and so on? We'll try to find out what is the condition for minima to occur. Okay, what is the condition for minima to occur? Let me tell you, from the concept of interference itself we will be able to do. We are not going to do rigorous mathematics. We'll just do little bit of we'll just recap what we know from interference. For destructive interference, see this destructive interference. So destructive interference will occur when the path difference delta is actually multiple of lambda by 2. So this is first. So we know this is for the first minima to occur. First minima will occur at lambda by 2. When path difference is lambda by 2, we know, right? N plus 1 or 2n plus 1, 2n plus 1 by lambda by 2, right? Or n plus 1 by lambda by 2. In this case, n has to be 0. For the first dark fringe to occur in the diffraction pattern. Okay. So here also we'll get minima. In minima means zero intensity of light, and that happens when there is destructive interference. And for happening this, or to get first destructive interference, we has to have minimum path difference between the interfering waves lambda by 2. Interfering waves lambda by 2. So this is actually important to know. So here we'll see in this figure itself. Look, we are trying to find out the condition for destructive interference. Maybe I'll just get another drawing. I'll just remove this part. I'll just draw. So we'll see here condition for secondary minima. Secondary minima. Or directly we can say, okay, condition for secondary minima. See, I have slits over here. Okay, this is screen. Now I have plane wavefronts like this. Since I am talking about Fraunhofer diffraction like this, so rays are parallel rays like this. Now see, I'll just take two representative waves. So this is slit, say, okay, this part is A, this part is this portion, this point is named as B. Okay, so from A, suppose a ray, so let me draw this horizontal lines. So after diffraction they get bent by an angle. Let me take this screen little closer. Okay, so it get bends and meet here. So this also get bends and meet here. Okay, from sorry. Okay, let us say this is the point P. This is the central point. So where we see the bright central bright fringe. Okay, central bright region like this, like this, central bright region here. Sorry. Central bright region, okay, like this. And then the minima occur. The first minima is this. Okay, say this is the first minima. Here the intensity is 0. Then you will get again say one maxima here also on the either side like this. You will get another maxima like this. It will occur. Okay, like this it will go. All right. So at this position, what is the condition that at this position the minima only will occur? So let us say these two rays, representative rays from the edge of this, like to the upper edge, from upper edge, this ray, let us say this is a ray R1 and this ray R2. They are interfering at this point P, and see how the angle of diffraction, see they got diffracted by angle theta. Okay, as I said, this they will be actually parallel to each other. We have made them to interfere or converge at this particular position after putting a lens in between. Okay, in between the screen and the slits. Okay, this is screen. So see, we had condition that lambda has to be first minima to occur, first dark fringe to occur in the interference pattern of Young's double slit experiment. The path difference has to be lambda by 2. Now, for these two rays, let us see what is the path difference. See, if I just drop a perpendicular over here, okay, if I drop a perpendicular over here, okay, this, suppose this is an is the normal, okay, on this ray BP. Okay, so I'll just tell you an is perpendicular to BP ray. Okay, an is perpendicular to that, so this angle is 90°. Okay, look, if I just draw this AB line, also AB line, I should have given dotted. Okay, this is actually open, sorry, this is opening here, so I'll give a dot here to join them. Okay, so look now from the triangle ABN. See the path length AP. See the path length AP and NP are equal. So if I want to have the path difference between this, so path difference between AP and ray BP, if I say that is delta, that is just the BN part. Okay, because AP and NP are equal. Okay, equal length, equal distances they are traveling. Okay, so path difference delta is actually Bn, but what is the length Bn? We have to find out what is this path length Bn. So for that, let us try to get this triangle ABN. At ABN, so this is actually a right angle triangle, because this angle is 90°. Since this, see, if this is theta, you look here, if this is theta, see, since this is perpendicular to this ray, so this angle will be 90 minus theta. If you agree with me, just tell me if you agree or not. So this angle, this particular angle will be 90 minus theta. Okay, this particular angle will be 90 minus theta, right? Now this is, see, this length AB will be 90° to this line, horizontal line. Okay, so this horizontal line and this AB will be perpendicular to each other. So to have this angle 90°, this must be theta. Okay, so what we have got now, then see, we have got BAN angle is theta. Angle BAN is theta here. Okay, theta. Now it is easy to find out. So this has length, so slit width is A. So I can write sine theta is equal to perpendicular by base, sorry, perpendicular by hypotenuse. Perpendicular is BN. BN is perpendicular. This theta angle is this one. So this is the base I am taking, and this is as hypotenuse. So BN by AB. BN by AB. Look, I hope you are understanding. So BN by AB is sine theta. Okay. So what is Bn? Bn is the path difference I need to find out. And what is AB? AB is A. So Bn is how much? Then Bn is equal to A sine theta. So this is actually the path difference between the two waves which are meeting or interfering at point P just after the central bright. Okay, central bright. Now this interference will be destructive according to our previous knowledge if so this point, in other words, point P will be a minima, first minima. P will be associated with first minima with first minima if this path difference Bn or A sine theta becomes equal to lambda by 2. Okay. Okay. I'm sorry, there is, I think, just a minute. Yes, this is actually condition. Okay, so condition for minima to occur. Just a minute. Actually, no, actually this thing is we have to just consider this path difference. When this path difference is lambda, then the diffraction first minimum will occur. Okay, this is actually an assumption. Actually, this is the way of analytical way of doing. What I was saying that delta is equal to lambda by 2. This is actually condition for destructive interference in case of Young's double slit experiment. That is fine. This is all right. But here, what we have to assume that the path difference between these two lights from the extreme 2 points of the slits have to be lambda. Then only the first minima will occur in this case. Okay, I'll just explain once again. So we have got the path difference here Bn, which is equal to A sine theta. So P will be associated with first minima if this A sine theta becomes equal to lambda. Okay, this is we are actually presuming. Okay, We are assuming this. Now we'll explain. Now we can explain how this point will be minima if this is satisfied. Okay, first minima. If this is satisfied. See, for this, okay, let me just erase things. So how P will be the position for the first minimum. Okay, okay, let us see if the condition is this. Okay, if the condition is a sine theta is equal to lambda, this is the condition for first minimum to occur in case of diffraction phenomena. So how we can explain this, that this is the really the condition. So this is the screen say. Okay, so as we had taken like this. Okay, these are two rays R1 and R2. So this is point A, this is point B, this is point, suppose this is the middle point. If I just take a middle point, let us take M. Okay, M, middle point. So we have seen, or we have taken the condition that if the path difference between these two like extreme points is equal to lambda equal to lambda, that is A sin theta is equal to lambda, then there will be minima, first minima occurring at this point P. But how is it possible? Look, when we divide these slits into two equal half, then see the path difference between this ray which is coming from A and the ray which is coming from this M, they will have path difference delta is equal to lambda by 2. I hope you agree, because the whole slit width will give you path difference. So A will give you path difference lambda, then A by 2, this will give you path difference lambda by 2. This is for sure. And see then what happens if we do this. Look, we'll have the path difference between the rays which are coming from this A point and M point. They will actually have destructive interference because path difference is becoming lambda by 2. Okay, this is the condition for destructive interference, right? Now I'll take another two rays, see which are. So if I just take this middle point of this AM, so this point will have a corresponding point here. Okay, corresponding point here at the middle, like at the middle of the lower half. They will actually interfere again destructively because they will have path difference again lambda by 2. If I take another point near to this and point near to this, corresponding point near to this, better if I just take, see, if this is having some if A is suppose 10, okay, 10, so 10 some centimeter or something, 10 millimeter or something like that. So in that case, you know, if I divide this into two half, see, upper half is 5 and lower half is 5. So between these 2 points, rays will have lambda by 2 path difference. Similarly, if I take this, see, suppose I take 10 points over here, because this have 10, so 10 points I can take here like this. Okay, so if I take 10 points, 1 2 3 4 5 6 7 8 9, 10. 10 points I take. So 1, 2, 3, 4, 5. So let us take this as the middle, right? So see, between this 1 and 6, I think, yes. So between 1 and 5, there will be path difference lambda by 2. Okay. Then, no, I'm sorry, 1 and 6 I have to take. 1 and 6 will have 6, then 6 is the middle I have to take. Okay. So 1 and 6, there will be path difference lambda by 2. Then 2 and 7, this is 6, so this is 7. Between 2 and 7, there will be path difference lambda by 2. Then again 3 and 8, there will be path difference lambda by 2. So when the this is actually 5 millimeter, this A is becoming A by 2. Okay, the slit width is becoming A by 2, equal to A by 2. If this is A, then if I just make into two halves, then both halves will be having like having distance. See, this is A by 2, this is A by 2. And if I make like that, see, if I just get some points here in the upper half and corresponding point in the lower half, then they will actually exhibit path difference lambda by 2, and they will destructively interfere. Okay, so this is the condition. So A is equal to, sorry, A sin theta is equal to lambda. At this condition, there will be first minima at this position P. Okay, so we'll just continue this discussion where to find like how to find out again the other minima also, like second minima, third minima, etc. We'll continue this discussion in the tomorrow's class also. Now we'll stop it here for today. So thank you for your patience. Bye for today.